I'm Greg Jacobs. I teach at Woodbury Forest School in Central Virginia. It's a boys' boarding school, and I would love your younger brothers to come be in my class in a day or two or a year or two, but not today. My classroom is empty and I miss my students, and I'm glad to have you guys behind the camera with me. Big news today. We now know the dates for the AP Physics 1 exam. May 14th, 4 p.m. Eastern Time. That'll be great. There will be 2 questions on the exam. There will be a 25-minute question and a 15-minute question. How will you respond to them? You will get them on a device, and then you have a choice. You can write the questions on a sheet of paper, take a picture, scan it, upload it. That's one option. If you do that option, I recommend unlined paper. That's the best way to go. The second option is to type directly into the browser. That works too. And either one of them is fine. All you're asked to do on any AP exam this year or any year is to communicate. Communicate your understanding of physics to the readers. As long as we see that you have communicated your understanding, and as long as your understanding is correct, you will get credit. You're going to have a lot of questions. I know that. You can go to the AP Central web page, the official page where the College Board has been posting all of the information about updated exams. That will be updated this afternoon, and you can take a look at that. Then you're going to have questions that say things like, will I get points off if if your question starts that way, please don't ask it. That's not the right phraseology. When I say we, I mean the readers. I'm an AP reader and have been so since 1999. And we are not Mrs. Hawkins, my 4th grade teacher. You see, she would look at some really good work for a 4th grader, and she would say, well, Greg, you did not spell this word correctly, and you didn't use a period at the end of the sentence. That's an F. She would. And that's not what we do. What we do as AP readers is we look and say, did this person communicate their knowledge of physics in order to get this point? And if so, the answer is yes. We are not lawyers. We're not going to say things like, well, this person typed their answer, and I know that angular momentum is I omega, but they typed a W instead of an omega. I don't know if they really mean what they think they mean. Of course, we're not going to say that. We're physicists and physics teachers. We understand standard notation. We understand what you're trying to tell us. So just let the communication flow and you will get the credit you deserved. Interestingly, of those 2 questions, the first one will be what we know as currently a typical 12-point question, the qualitative quantitative translation. That's just a question that involves equations and physical conceptual reasoning and the connection between the two. I'll do one of those problems or something similar to one on Monday when I talk about kinematics and the definition of acceleration. The second problem will be a paragraph problem. I think of paragraph problems as just a long version of justify your answer. Paragraph question should be answered in words. You can reference equations, but any equation needs to be part of a sentence that has a subject and a verb. That's all we need. I've been talking about how to answer such questions every time I've been doing one of these things, and I'll answer them I'll do some more of those in the weeks to come. But a paragraph is just explaining your answer in the same way I explain the answers to these questions. All right, let's get started here with today's discussions. If you would like to follow along on @JacobsPhysics, I'll answer questions toward the end. We're going to start with the question from Thursday, and we'll get to how to know whether to use kinematics, Newton laws, momentum, and energy. That was my original monologue, but that got trumped when we decided that we are going to use, or that we're going to find out what's going to be on the exam. All right, so let's go on to the question from yesterday. We've got the pivoted rod, and we want to know what is the angular momentum of the rod immediately after the collision. This time the ball didn't stop after the collision, the ball bounced off. How are we going to do that? Let's go to the board here. And let's do exactly what we did yesterday, except this time the rod is pivoted there. The ball's coming in this way. We know that the initial angular momentum, the angular momentum before collision, is equal to the system angular momentum after the collision. The angular momentum before the collision is the angular momentum of the ball plus the angular momentum of the rod. The rod has no momentum before the collision. It's not spinning. The ball has a momentum, and that is MVR. We talked about that yesterday. The angular momentum of a point object moving at steady speed is MVR. What is R? Well, R was given in the problem as this distance, D. And MV isn't given in any of those answers, but we should recognize MV as an expression for linear momentum. They called that B. So beforehand, the linear momentum of the ball is this. All right, after the collision, the ball bounces back off in the other direction. So the ball's linear momentum, or the ball's angular momentum, is PF times D, MVR, where MV is the linear momentum, and D is that distance of closest approach. But now the rod has angular momentum as well. And that's what the problem asks for. We subtract these two after the collision. Why? Because the rod and the ball after the collision are rotating in opposite senses. That's why we subtract. Angular momentum is a vector. Angular momentum is in the same sense. Add, in opposite senses, subtract. So let's solve for what the problem asks for. And that, friends, is choice D, which I will share with you now. If you have questions about that, feel free to stick them on Twitter @JacobsPhysics. And now we're going to go into forces in equilibrium. Screenshot this if you want to. You can refer back to it. If you want to go to Google Jacobs Physics Just the Facts, you can download my fact sheet and you can follow along there. We're going to be talking about forces in equilibrium. This, for reference, is the very first topic that I cover in my AP Physics class. In fact, this is some of the stuff that I do on the first or second day of AP Physics. Now, I mentioned this because you guys have probably covered forces in equilibrium in your own physics class. There are a lot of different ways of approaching force and equilibrium problems. I might be doing something that's very different from what your teacher taught you. That's fine. You can do it your teacher's way. You can do it my way. It makes no difference. Remember, the AP readers are people, not robots, and we are physicists, not lawyers. We will understand whatever you're trying to communicate, as long as it's communicated clearly and it's right. So let's start with the simplest problem I can possibly imagine. I have a 200-gram object, and it is just sitting here. I want to draw a free body diagram for this object, and I want to predict what is the tension in this rope. Let's start with a free body diagram. Free body diagrams, or force diagrams you might have called them, indicate all the forces that are acting on an object. The forces must start on a dot that represent the object and point away from the dot. That's a requirement of the exam. When you are drawing a free body diagram, start with the force of gravity. Which way does gravity act? Yep, still down. So we draw an arrow down. I label that mg, and I'll explain why that is. And off to the side, this is not required for the AP exam, but I strongly recommend that you do this. Off to the side, I recommend that you define each force. Forces can only be exerted by objects on other objects. So it is worth writing, what is this? The force of what on what? I know that all of you are saying the force of gravity on the object. Gravity is not an object. Only objects can exert forces. What object exerts the force of gravity that pulls this thing to the ground? It's the whole Earth. The force of gravity that you know of is the force of the Earth on the object. Okay, what other forces act on this object? After gravity, any other force in AP Physics 1 right now requires contact. The only other things that can act on this block are the things that are touching the block physically. So what else is touching the block? There's only one thing that is touching the block right now, and that's the string. Which way is the string pulling? Upward. Strings can't push. So I draw an arrow upward. I'm going to call that T for tension, but I'm going to write over here, T is the force of the string on the object. Now, why am I saying that you should write the force of what object on what object? Well, there's a variety of reasons. One is it makes Newton's third law questions trivially easy. What's the Newton's third law force pair to the force of the string on the object? The force of the object on the string. What is the Newton's third law force pair to the weight? Well, weight is the force of Earth on object, so the Newton's third law force pair is the force of the object on Earth. Okay, great. Another reason is because that helps the reader interpret what you've written here. Many of you will have written something like F sub G or F sub W or W for weight. That's all fine. But if you write something like F1, that's sort of ambiguous. I don't know what that means, but if you write off to the side F1, force of the Earth on the object, oh, okay, suddenly that's very clear. T for tension, doesn't matter what you call that as long as you define that as the force of the string on the object. But we understand tension, force of the string, F sub S, whatever you want to say. What other forces are acting on this object? There are none. There are none. The reason I have banana written on there is there's a famous quote by Terry Pratchett about one of his characters. He says that Nanny Ogg knew how to spell banana. She just didn't know how to stop spelling banana. There's a lot of you all who know how to draw free body diagrams. You just don't know how to stop drawing free body diagrams. Once you see that you have indicated a force for everything that is touching the object, you're done. This object is in equilibrium. That is, it is moving in a straight line at constant speed, or it is remaining at rest. When something is in equilibrium, we write up forces equal down forces and left forces equal right forces. In this case, the tension is equal to mg. In this case, m represents the mass of the object and g represents the gravitational field. The mass of this object is 200 grams, which is 0.2 kilograms. G is the gravitational field of 10 newtons per kilogram. So the tension here is 2.0 newtons. That's a trivially easy problem. There's a reason I'm doing it. Part of that is to show you that we can measure that tension. We can measure what we predicted, and this scale, I know you can't see it, but I'm seeing it right here, and I do this every year, so 25 years worth of students will tell you that this scale reads 2 newtons. But now let's do a more complicated problem. This is a 100-gram object, so it has a weight of 1 newton, and the tension in this string will be 1 newton because it's going to be in equilibrium. There we go. There we go. Yeah, this is off there. Good. So this is pulling straight down. This is horizontal. I checked beforehand. This string is horizontal, and this string is at an angle. And the question is, what is the reading in the scale now? What is the tension in this rope? That's not a trivial problem. But how do we start? It's a force problem, right? Well, force problems start with free body diagrams. I can't tell you how many times in the first weeks of my class, somebody comes to me and says, Mr. Jacobs, I'm so confused. What do I do on this problem with forces in equilibrium? And I say, well, let me help you. Show me your free body diagram. And they say, well, I don't have a free body diagram yet. I'm too confused. And I said, well, go away, go draw a free body diagram and follow the steps that we've talked about. And then when you come back, I'll be glad to help you out. And they go away and they don't come back because I go follow them later and say, hey, you were struggling before. Can I help you with that problem? You know what they say every time? Don't worry, Mr. Jacobs, I got it. Draw the free body diagram is the point. What do we got here? I told you to always start with gravity. We're doing a free body diagram for this object only, please. This 200-gram object. That's mg. That is the force of the Earth on the object. Well, now I've got two strings touching this block. So I need to have two forces representing the two different strings. One is this way. I'll call that T1. And one is this way. I'll call it T2. T1 is the force of string 1 on the object. T2 is the force of string 2 on the object. Now, I told you the next step when an object is in equilibrium, which this thing is to write up forces equal down forces and left forces equal right forces. So that means the left force, T2, is equal to, I don't have a right force, and mg is the down force, but I don't have an up force. What do? We go to step 1A. If you go back to that, to the facts that I showed you, you will find that step 1A is break angled forces into components. Once I've drawn my free body diagram, I redraw the free body diagram. Don't put components on the same diagram as the force itself. I redraw the entire diagram. T2 and mg are their own components. I have T1 in the horizontal direction, and I have T1 in the vertical direction. Any force can be expressed as a horizontal component and a vertical component. That's all I do. It really is that simple. Now I can write up forces equal down forces and left forces equal right forces. I'll go over here. Left equals right and up equals down. Now we got to do some thinking. I know T2 is 1 Newton. I told you that. The tension in this horizontal rope is 1 Newton. I told you that. And I told you that mg is the weight of this 200-gram block, which is still 2 Newtons. We're still on Earth. So let me write that out here. So I know the horizontal component of T1, and I know the vertical component of T1. But the question asked, what is T1 itself? And that's not 1 Newton, and it's not 2 Newtons, and it's not 3 Newtons either. How do we figure that out? Well, this will help you. T1x is the horizontal component of T1. That was 1 Newton. T1y is the vertical component of T1, which is 2 Newtons. So now if we look at this, we're asked to find T1 itself, which is at an angle. Once I put it this way, all of you are remembering in geometry, oh, we just used the Pythagorean theorem to find T1. And you're going to also tell me that that's the square root of 5 Newtons. Well, the square root of 5 doesn't show up on this thing, but if I take the square root of 5 on my calculator, I get 2.2 Newtons. So T1 is 2.2 Newtons. I can also answer, I can ask another question. Let me first verify that, yes, the scale here does read 2.2 Newtons. Once again, you can't see it. Ask anybody who's ever been in my class. Ask the teachers who have been in my institutes. I have somebody come up from my class, walk up to the front of the room, and read to the class, and it's 2.2 Newtons. I could also predict this angle here. Call it theta. I can just use straight up trigonometry. This is just a triangle. I can say that the tangent of an angle is opposite over adjacent, so that's 2.0 Newtons over 1.0 Newtons. If I plug into my calculator and take the inverse tangent of that, I get 63 degrees. Is that right? I'll measure that and I'll show you it's right. What I have here is an angle indicator. I don't think you can see the numbers there, but you can see that this is giving me different numbers and a different gauge every time I twist my phone. So if I put my phone along here, I know you can't see this, so I'm going to make sure I can see it. It reads 63 point something degrees. Physics works. All right. Let's go to one more problem with this. I'm going to change this up. I'm going to place a mystery mass on the edge here. Now I'm going to rejigger my setup so that this rope is horizontal. And then I have to rejigger my setup so this isn't touching the pulley. That means I'm going to pull this out here. I'll tell you, this collapses maybe once out of every 2 times that I do this. There we go. And let's make sure that this is as close to level as we can get it. Yeah, within a degree of level. All right, I have a mystery mass here, and I have a scale reading here. I have a 200-gram object hanging, and I'm going to tell you that this is at an angle of 37 degrees. The question will be a variety of questions. The mathematical question will be, what's the reading in the spring scale and what is the mystery mass? But I want to start with a simpler question. I want to know, is this mystery mass greater than, less than, or equal to the 100 grams that I had previously? That we can answer quickly. In the first situation, I had this. In my new situation, the vertical component of this rope's tension still has to be 2 newtons because this thing still has a weight of 2 newtons. But horizontally, there's a lot more force because this angle is more like 38 degrees. So this has to be bigger than 1 newton. That's a good AP Physics 1 question to ask, is this mystery mass greater than, less than, or equal to the 100 grams I had before? Is the tension in this rope greater than, less than, or equal to the 1 newton it was before? I can answer that with just 2 little pictures, or I can answer that with trigonometry, which I'm going to do in just a moment. Physics 1 will not often ask you to actually get numerical answers. I'm going to do a numerical problem because I want to show you that I can predict this mystery mass just by knowing the angle here, and that's all and the weight of this thing, that's all I need, and because it's going to give you a technique of using the angle and the sines and the cosines in my setup. So my free body diagram is the same as before. I've got T1, T2, and MG, where those are all the same as I showed you there. I break up angled forces into components. So I still have T1x, but I have T1 cosine 38 degrees, or 37 degrees, I said. And vertically, instead of writing T1y, I'm going to write T1 sine 37 degrees. Folks, it is useful to memorize when you are breaking an angled force into components. As long as you measure from the horizontal component always goes with the cosine. The vertical component always goes with the sine. That's just something to memorize, I think. And I measured my angle from the horizontal. That's 37 degrees from the horizontal. Therefore, I can do that. Now, I can write left equals right and up equals down. I can write up equals down. And now I can stop and take stock. That's all that I'm supposed to do for equilibrium problems. Everything else is math if I know that I have enough information to solve. Do I? What was I asked to solve for? I was asked to solve for the tension in this string, that is the reading in the spring scale. That is T1. That's an unknown. I was asked to solve for the tension in this rope to get the weight of the hanging mass. That's T2. I have two equations. That means I can have no more than two unknown variables. Well, I have two unknown variables, T1 and T2. Everything else had better be known. Do I know the cosine of 37? Yes, I can plug it into my calculator. Do I know the sine of 37? Yes, I can plug it into my calculator. Do I know mg? It's 2 newtons. Therefore, the physics is done. The rest is just mathematics. Now, in terms of your AP exam, an AP exam is very likely to say, is this problem solvable? Explain why. And you would have to use equilibrium conditions to show that I can write two equations and two unknowns and everything else is known. This year's AP exam in particular is unlikely to ask you to solve a problem like this numerically. Why not? Well, for one thing, we don't usually do two equation, two variable problems. I mean, this one's trivially simple to solve for T1, but also this year in particular, in 2020, we are not asking any questions that would require use of a scientific calculator, that is sines and cosines. You need to understand that sine and cosine go here, but you aren't going to be asked to calculate a sine or a cosine. That's either going to be given or just not important. We just need to understand that this is solvable. You want to go home and solve it. You should get that the tension in one of the strings, I did this yesterday, the tension in the string should be, I believe, the tension of the string should be 3.1 or 3.2 newtons, and the hanging weight should be 2.5 newtons, so 250 grams hanging here. Do the math, see if it works. I bet it does, because physics works. All right, we have time for one more demonstration. And that's going to be with friction here. Let me take this down. One question that I'm sure to get is, wait, my teacher told me not to write left equals right. My teacher told me that I'm supposed to write left minus right equals 0. Well, that's the same thing. My teacher told me that left forces are negative and right forces are positive. That's fine too. I choose not to use negative and positive signs. I choose not to give my students negative signs, because what's a negative force anyway? That's hard to understand what that means conceptually. I choose to say all forces are just numbers. They're just values. And then we set left forces equal to right forces. This is all equivalent, but if you're used to doing things a different way, more power to you. All right, last problem here. I have a 90-gram boat and I have a force probe. The force probe is going to read here, and I'm going to let you see what the force probe reads in just a moment. I'm going to record the force as a function of time once I start this going. That's what I'm going to do. And now I'm going to take you to this screen, and you're going to see the force as a function of time. Okay. You can't see the numbers here, but you can see that I have a straight line graph here, and this is the 0.5 newtons line. So that force, if I actually press the button there, that force is something like 0.37 newtons. 0.36 newtons, excuse me, 0.36 newtons. That's the force of the rope on the boat. I'm not telling you what I want to figure out here. I'm just going to tell you about the force of I'm just going to ask for a free body diagram of the boat. This is the boat. What do we got? Well, we always start with gravity. mg is the force of the earth on the boat. What else we got? What else is touching the boat? Well, the string is touching the boat. The force of the string on the boat. I'm not writing this out because I'm getting short time here. The floor is touching the boat. we call that a normal force. The force of a surface on an object perpendicular to the surface, we refer to as a normal force. It's just the force of the floor on the boat. And then finally, we have a friction force because this is a rough surface. The force of friction is also the force of the floor on the boat. Yes, the floor exerts two forces, one perpendicular to the floor and one parallel to the floor. Was this object in equilibrium? Yes, it was, because it was moving at a constant speed in a straight line. Therefore, I can write two equations. Left equals right, and up equals down. Let's define the coefficient of friction, mu, as the friction force divided by the normal force. In this case, the friction force was equal to the tension, which was 0.36 newtons. That's what I read on my scale when I touched that. We know that the normal force is mg, that is the weight of this 90-gram block. That's 0.90 newtons. So the coefficient of friction is 0.36 divided by 0.9, which is 0.40. No units because the units of newtons cancel. The coefficient of friction represents a number that tells us how sticky two surfaces are. The coefficient of friction between my boots and a rug is much bigger than the coefficient of friction between my boots and ice. So now, last problem I'm going to do. I've got a 200-gram object, and I'm putting it in the boat. And I want to know, what will the reading in this scale be? What will the tension in this rope be when I pull this again at constant speed? Now we're going to go through and answer this question. But before we do, I want you to start with a what is the same question. In the equation, mu equals FF over Fn. Which of these variables stays the same? We have to ask that because a lot of people will say, well, the coefficient of friction goes up because there's more weight and therefore the normal force goes up. Oh, I'm sorry, the coefficient of friction will go down then because this is an inverse relationship. There's a lot of people who will tell me that it obviously takes more force to pull a heavier object, which it does at a constant speed here. So the coefficient of friction has to go up because that's a linear relationship. And then there's more people who will say, well, both the friction and the normal force go up. So the coefficient of friction, we don't know what happens to it. None of those answers is right. The coefficient of friction, in fact, doesn't change. How do we know that? Because that's one of our facts from the fact sheet. The coefficient of friction is a number that depends on how sticky two surfaces are. The coefficient of friction depends only on the surfaces in contact. Since this is still cork on a Formica surface, that coefficient of friction is always going to be 0.40. It's a coefficient of kinetic friction. We can talk about the coefficient of static friction some other time, but even that is a maximum that depends on the surfaces in contact. So I can redraw my free body diagram now. It's the same diagram. I have the same situation where the normal force was equal to the weight, where the friction force was equal to the tension. I'm asked for the tension, so I need to know the friction force. The friction force is equal to mu times the normal force, which is mg in this case. Well, now mg is not just the weight of the 90-gram boat, but mg is the weight of the 290-gram boat. mg is 2.9 newtons. The coefficient of friction is the same as it was before. So we are going to predict that the force of friction is somewhere between 1.1 and 1.2 newtons. So let me put this out nice and big. Here is our original situation. In our new situation, we should have a force of friction up here. Let's try it. Look at that. Right where we expected. 1.2 newtons the second time, 0.4 newtons the first time. The last thing I'm going to do is I'm going to slow this down. Still keeping the 200 grams in here. I'm going to slow this down. What happens to the force of the rope? Slowed down. So obviously I have to use less force, right? Of course. I should still get 1.2 newtons. Please don't troll me on Twitter right now, by the way. I should get 1.2 newtons. So there's my red 1.2 newtons, and I'll overlay these in just a moment. Let's collect. I'm going to let this go with a slower speed. Oh, wait a second. Oh, crap. I'll do it again. I just lost my, just lost it. Let's do it one more time. This is a slower speed, so of course I should get less than 1.2 newtons. And here's what I got originally. And here's what I got at the end. I got the same force. I got the same force. Now, wait a second. How come I still pulled with 1.2 newtons, even though this was going slower? An object is in equilibrium if it is moving in a straight line at constant speed. The thing was still moving in a straight line at constant speed. It was a slower constant speed, but we never said anything about the speed mattering when we set left forces equal right forces and up forces equal down forces. And sure enough, that speed doesn't matter. In my class, I have everybody bet a cheeseburger on whether the force is going to go up, down, or stay the same. And usually one or two people win a whole bunch of cheeseburgers in that class. It's a lot of fun. All right. That's enough demonstrations for now. I am on Twitter at Jacobs Physics, and now is the time to ask me questions. I'll take questions for 5 or 10 minutes. If you have a boat like the one in the experiment, says Mithri, and it goes from one material to the other, how would you incorporate the change of coefficient in your answer? You would probably do 2 problems. You would do one problem for when the boat was on one surface and one problem when the boat was on another surface. And just compare the two. This letter here is a Greek mu. If you need to type it for some reason, like you're taking an AP exam, just type the words or the word mu. It's a Greek letter mu. That's totally legitimate. We will know what you mean. Is it necessary to differentiate between the coefficient of static and kinetic friction? Not in this case, because everything was kinetic. There is a coefficient of static friction. The coefficient of static friction is always larger than the coefficient of kinetic friction, and static friction is really complicated and weird. The coefficient of static friction is a maximum value. The maximum coefficient of static friction I calculated earlier today, and it's something like 0.6. So right now, we can't pull Bertha, or we can't pull Edna. Bertha's at home right now. We can't pull Edna because the force of friction here is not enough to overcome the coefficient of static friction. However, if we could get her started, if I can get her started, then I can get her going at I might be able to get her going at constant speed. Well, I guess I can't, because I guess she can't, the force necessary here is, oh yeah, because I still have, yeah. The force necessary is still greater than the coefficient of, and the force of kinetic friction as well. But the force of static friction just tells us the maximum value that the coefficient of friction can take before the objects start to slide relative to one another. Usually you'll be in one situation or the other, and you can just decide which one is necessary. How did I know that the coefficient of friction was FF over FN? That's a definition. That's from Yan. Yan, just look on the fact sheet. The force of friction is coefficient of friction times the normal force. That's a definition. let's move on over here. Until when will we be continuing to do live classes? This is from Shahad, and they have a second question as well. We will continue live classes at least until the beginning of May, and probably there will be something going on maybe up until the exam. We haven't worked that out yet, but we are definitely going till the end of April, beginning of May. Josh or I on every day at noon. I know that on Monday, I will be here and I will be talking about motion. I will be talking about kinematics and the definition of acceleration. Josh is on Tuesday. I forget what he's talking about. If you check back by Monday, sometime before Monday, we will have all of the lessons posted for the rest of the month until the end of April. Their second question is, what is the percentage for a 5 on the AP Physics 1 exam? That's a great question. It changes year to year. Typically, historically, in the 5-year window we've had, in the neighborhood of 70% or so gets you a 5. In the neighborhood of 40% gets you a 3. That could change depending on the difficulty of the problems. And that could especially change this year where there's only 2 questions. That could go way up or way down. We don't know. There will be a standard setting, which is a very complicated way of figuring out what the standards are. Suffice it to say that the goal is that a 5 means the same thing every year since 2015. Doesn't mean the same percentage. It just means the same level of achievement every year since 2015. And they'll try to do that again this year. We still have time for 1 or 2 more. Oh yeah, why was there not a normal force on the hanging object that we were starting with? And that was from Nishtha. And thanks to Brad Williams, he already answered this, but I know that more people have that question. A normal force does not mean a typical or a usual force. That's not what normal means in this context. Normal in this context means mathematically, it means perpendicular to the surface. A normal force is the force of a surface on an object that acts perpendicular to the surface. Since this thing right here is not on a surface, don't put a normal force on there. Only put the weight and then a force for any object that is in contact with this thing. Only the rope is in contact. So that's all we got. If I were to push up as well, then we have the force of my hand. If I were to push down, we'd have the force of my hand. But the only forces that can act are the ones that are experienced through contact, with the exception of gravity. And we still have lots of questions. Understand that I'm going to be on Twitter for a good half hour to an hour, and I will continue to take these questions and try to answer them there. Sarah asks, does a qualitative quantitative reasoning question potentially include things like experimental design or drawing graphs? I don't know. I really don't know. There will not be a focus on experimental design because that's an entirely different type of question. Could one part of the question ask something very quickly about how would you measure this, or a measurement in a probe? Sure. Would it involve drawing graphs? As I don't know. I can't say because I'm not on the development committee, and if I were, then I definitely couldn't say, because then the College Board would have some capital W words with me in the basement of a dungeon. I don't know. I doubt there's going to be too much with graphs because it would be hard to input, but maybe you could. That's one of those open questions right now. And finally, can you include components on the official Freebody diagram answer? That is interesting because there's some history here that you'll enjoy. The history is, for years, there was no real rule about whether you could include components on a Freebody diagram. And I remember one year in the refreshments tent in Colorado State University, I had a 3-hour argument with another physicist about whether components should or should not be included on a Freebody diagram. This went on, and people were coming in and watching the arguments and leaving the argument. Note that I had not had any refreshments that night. I was simply having the argument. Anyway, the next year, the College Board's development committee came out with a statement that says, do not put components on Freebody diagrams, period. The problems will say, include the forces, but not components that act on the object. I think that's coincidence, but I like to think somewhere back of my head, somebody on the development committee said, oh my goodness, I wish these two folks would stop arguing. I'm just going to make the statement. So no components on free body diagrams. All right, that's enough for today. I will be back with you on Monday, and here's the question that we will be working on Monday. This will be available on YouTube after today's show. It's actually 2 questions, multiple choice. The first is to show me the relationships between 3 tensions that are there. And the second one is to explain why the normal force on this particular block is less than 7 newtons. I'll start Monday's show by answering these questions, after which I will go into kinematics and the definition of acceleration. I hope you'll consider watching again. I'm thoroughly enjoying conversing with you all on Twitter and over our show at Jacobs Physics, jacobsphysics.blogspot.com. It's been great talking to you all. Say goodnight, Edna.